Okay, so I'd like to thank everyone for joining in. My name is Justin Patucci, and I am a staff member over at the Institute for Computational and Data Sciences. So ICDS, as it's known. ICDS is an interdisciplinary research institute within Penn State's Office of the Senior Vice President for Research. We build and maintain Penn State's largest high-performance computing system, and we offer various services and training centered around that high-performance computing system. Today, we're going to be talking about a sort of host of different high-performance computing aspects in this installment of the Roar training series. So first off, in this title slide, you can see a link to the slides, right? And I'm just going to sort of put that into the chat again for our sort of, if anyone is just joining. So with that, I will begin. So here we see an overview of the session for today. We're going to talk a little bit about version control with Git, code optimization, different things that you can do as just a general user running someone else's code or someone writing their own code. Then we're going to have a hands-on example where we sort of tie a bunch of different things together, version control with Git, build automation with Make, debugging with GDB, and profiling with gprof. Then we'll touch on some different aspects of parallelization with shared, distributed, and multitasking parallelization. And then we'll wrap this up with a discussion on scaling studies, why they're useful, what they are. So goals for today, obviously align with those, with the content, to learn a little bit about version control and some optimization basics, learn about the different types of parallelization, and learn about scaling studies. So I'm the only sort of staff member here today, but if anyone has any questions, feel free to unmute yourself and directly ask the question or put it in the chat, and I will do my best to monitor that. I think we have a very small crowd today, so if you're okay with unmuting yourself and just sort of stopping me at any point, that would work the best. And I have this in sort of almost every presentation that we give as part of this training series, that experience really is the best teacher. So we'll go through a bunch of different examples, and it can certainly be to your benefit to sort of go through them now and then also on your own time to help sort of solidify some of the concepts. So before we delve into the actual content, we're going to set up for our hands-on session. And the way that we're going to do that is using our Open on Demand web portal. So and this requires you to have an account on our system. So hopefully everyone has an account on our system. So the first thing you want to do is open up your favorite web browser, I think Firefox, Chrome preferred, and then navigate to this website, portal.aci.ics.psu.edu. Log in with your Penn State Web Access credentials, and if you haven't gone through Duo yet today, you'll have to do that. And then eventually you'll land on our sort of landing page for the portal site. So I'm going to pull that up on my end now. So the portal site, again, it's portal, and hopefully everyone can see my web browser now. I should be sharing my entire desktop, but if you cannot see my web browser, please let me know. Again, go to portal.aci.ics.psu.edu, log in, and then once you're logged in, we're going to sort of use this menu bar up top, and we're going to go to Interactive Apps and ACI Interactive Desktop. So as a way of sort of normalizing everyone's software environment, we're going to use a sort of graphical desktop job on the Roar systems. And we can do that, we can start that job by filling out this web form. So for the desktop environment, select GNOME 2. For the allocation, if you signed up for this training ahead of time, you should have access to this training allocation. So WFF3_G_G_LC_ICDS training. So hopefully everyone has access to that. If you don't, it's okay. Select the open allocation. So I'm going to sort of proceed like everyone has access. For the number of hours, just put, 2. That'll get us well beyond this training session. And then for the node type, select standard core. Once you have that filled out, hit launch. And what that will do is behind the scenes, that will kick off a job. It'll create a job script, send that to the scheduler, and the scheduler will find a place to run your job. You'll have this sort of this rectangular box that shows up with some details about your job. Up top in that box, it'll be gray and it will say queued. Once your job starts, that will turn green, and you'll have a little button to click here to launch your job. So I'm going to delete my job just because I already have one running, and I don't want to take resources away from anyone else. But sort of, we'll let your job sort of sit there for a couple minutes, and then hopefully when it comes time for the actual hands-on sessions segment of this training, your session will have started. So I'm going to switch back to the slides now. If anyone's having trouble submitting that job, please let me know. Okay, so our first item that we're going to talk about is version control. So what is version control? You can think of version control as a way to track multiple versions of a particular code. So I know a lot of people, when they first start out with writing code, their sort of idea of version control is to sort of rename files locally, maybe with a date stamp or some sort of indication that a change was made. Every day you sort of, code name version 1, at the end of the day version 2, that sort of thing. And that can quickly get out of hand, and really as soon as you get burned by that, by sort of not being able to sort of make sense of changes, or a conflicting change, or just maybe losing files, that's usually when people start to think about adopting a implementation of version control. I know I certainly fall into the camp of someone who used to sort of just date stamp everything and then, happily go along. And then eventually 6 months down the road, you really can't make sense of changes that were made. And, maybe you have to go back to a prior version of the code. And like I said, it can really get out of hand. Version control doesn't have to be just code. You can version control really any file. This presentation is version controlled. Version control can be useful both for the development of code, especially whenever you have many people contributing to a code base. It can also be helpful whenever there's different variations of code. Maybe you have different versions of code that targets different types of hardware, or maybe different variations of code serve different purposes. So these are all things that can be easily handled within a version control system. So there's many types of those systems out there. So, what is known as the local data model. So these are sort of and as we sort of talk about these different types, it sort of follows the history of version control. These local data model sort of solutions were the earliest types of version control, and then the distributed model are sort of the newer version control systems. So, under the local data model, this is very similar to storing everything on your local machine and really changing the date, changing the files locally. With the client server model, there's one master repository. So everything that's sort of in production is in that sort of master repository, and then there's different development points sort of scattered in different locations outside of that master or main repository. So local machines make changes and then push that up to the main repository. So SVN is a example that's still in use that follows this client server model. Under this distributed model, there's no master or main sort of repository or development point. Sort of every local repository has its own main repository. So Git falls into this distributed model. And a lot of times Git is used sort of as a client server model, but it does have the ability to have, no main sort of master repository, right? Everyone can be the main and no one can be the main sort of thing. So for our purposes and for our hands-on training here today, we're going to focus on using Git. So why do we do that? It's incredibly flexible. It's very widely used, and it has great documentation. So with Git, there are 3 typical steps within the Git workflow, and that's really saving. Modifying your files, saving those files, and then sort of taking a snapshot or really sort of committing a particular version of your files. And we're gonna see this in sort of in explicit detail once we go through our hands-on example. So the basic Git structure. So Git uses something called branches, and these different branches can serve different purposes. Mostly all Git repositories have what is called the master branch, now renamed to be main by default, I think, on GitHub. And this is traditionally where the production version of the code base lives. And most of there's many different sort of branching workflows that people can fall into. If you're sort of a single developer, what most people fall into is they have a main or master branch where production lives, and then they sort of have a development branch, and that's where you work to sort of make changes to code and develop the code. And then once a change is ready to move into production, everything is sort of just copied over into the main or master branch. Git flow is another, is a popularly used Git sort of branching model. And that's something that I encourage you to look up as you sort of become familiar with Git. I mentioned that Git is under this distributed model. So there's no primary location. Everyone sort of can pull, to different locations as required to keep everything in sync. And again, we're going to touch on a lot of these items once we get into our hands-on example. So I'm not going to sort of go through each item on these slides. It's more for your reference to sort of go back and maybe sort of, in my experience, it's good to sort of be exposed to Git sort of in a hands-on fashion, just to see sort of the basic workflow and to see how it works, and then sort of go back and sort of read up on it and dig in deeper in the areas that you need to. Some basic Git commands that we'll run today. So clone is making a copy or exact replica of a repo. Pull and push is how you can make changes, take your changes and make them. So if you make changes locally and you want to push those changes, make those changes at a remote location, you use push. If there's something if there are changes that were pushed up from a different remote location, you can pull those down with the pull command. Init is how you initialize a new repo, and so on and so forth. We'll be using mostly all of these commands today. So again, this can serve to be a reference for you. I mentioned that Git is widely used. So GitHub is a sort of web-based implementation of Git. So it has Git, and then it has sort of this web-based front end on top. So that's something that you can use to remotely store your Git repositories. Penn State also has a GitLab instance, which is available at git.psu.edu, and there's other online repositories as well, and then some places to get some documentation. So git-scm and obviously GitHub are great locations for some additional resources. And then this Git flow branching model is something that you can look into as well. Any questions about Git? That was sort of really just a little flavor about its purpose. Not too many details about how you use it in practice. Again, we'll see that here once we jump into our hands-on session. Okay, so just skipping along in my notes here. Okay, so moving on to the code optimization or sort of code performance portion of today's session, and this really is the bulk of what we're going to be sort of focused on today. And it's really, getting your code running and running well are certainly different things, but ultimately they're linked together. So we're going to look at some different ways that we can help us as the user, you as the user, determine what parts, what part of the code could use some help. So to that end, the first thing you need to do is determine, is your code giving you the correct answer? So, if that's not the case, then that obviously needs to be sort of immediately addressed. After you sort of confirm with some reference cases that your code is, giving physical output that, matches up to some reference case, then you can start asking the question, is it performing well? Is your code fast? And with that question, comes other questions. What part of your code is taking the most amount of time? Is there anything sort of what I call low-hanging fruit that the compiler can do for you automatically to speed things up? Next question could be, is there some way that you can expose some parallelism in your particular algorithm so you can take advantage of, some type of parallelism, which we'll talk about later, maybe distributed parallelization or multitasking parallelization. Is there something, inherent in your algorithm that you can sort of utilize parallelization for? And finally, are you doing something where an optimized library exists and does it better than you could ever do? So, we're going to go through an example with matrix multiplication, obviously sort of ubiquitous across disciplines and across areas of science. And many vendors such as Intel spend a lot of time and money optimizing linear algebra. So, if you're doing some basic linear algebra operations, it may be to your benefit to just use a vendor optimized library rather than trying to write that yourself and going through the pains of getting that running and running well. So, for this, obviously, it's great to have that reference case or those sort of those test cases that are reflective of your production runs that you know the answer to. And you want those test cases to be small enough that you can sort of iterate on them quickly. But at the same time, they have to be large enough that they are sort of representative of what you'll be running in production. So in theory, this act of debugging and profiling are separate, right? So debugging is getting that correct answer, and profiling is identifying hotspots in your code and then making changes in the code to accelerate or make those hotspots perform better. But in practice, they're inherently linked, right? So maybe you start by profiling your code, you find a particular part of your code that's taking a lot of time, so you make some modifications to make that part of your code run better, and then all of a sudden you may introduce a bug, or introduce something that makes the answer not come out correctly. So this profiling and debugging sort of happens in response to each other. So we're going to go through here in a moment, not the next slide, but the slide after that, sort of a process for you to sort of follow, where you start with simple things first and sort of move upwards in terms of complexity and effort on your end to sort of go through this process of making sure your code is running and then getting your code running well. So really the first step in that, and that's why I call this sort of the free lunch slide, is essentially taking advantage of what the compiler can do for you for free. And by free, I mean really all you have to do is put an additional compiler argument in there, throw a compiler flag, and you could see a pretty significant performance increase, by essentially doing nothing. So compilers have a lot of built-in functionality which can be used to improve the runtime performance of the code with, again, very little effort on your part. So this slide represents sort of the minimum low-hanging fruit options that you should at least try. So first up for that is most compilers have what are called general optimization levels. So typically these come with different levels. Levels 1, 2, and 3 are pretty common across different compilers. And these different levels consist of many different individual optimizations, such as function inlining, unrolling of loops, etc., that the compiler will try. And as you increase the optimization level, the optimizations that are attempted by the compiler become more aggressive, and they take more time. So I'm going to switch over to my browser now just to give you an idea of sort of what I'm talking about here. So hopefully you can see my my browser here, and I'm on a website for the GCC GNU project. And this is about different optimization options that their compilers have. And right now I'm under the sort of general optimization levels. So we can see this optimization level 1 actually is sort of shorthand notation for all of these different optimizations. And then we sort of walk our way up to optimization level 2 is shorthand for all of these optimizations plus anything that optimization level 1 does. And then sort of optimization level 3 is similar. Here's some more optimizations that the compiler tries, plus everything that O2 level tried, and then plus everything that O1 tried. So these optimization levels are really just shorthand notation for a bunch of different optimizations that the compiler is going to try. So for you as someone compiling code, whether you wrote the code or not, something very simple for you to do is compile the code with these 3 different optimization levels, right? So try compiling with optimization level 1, 2, and 3, and run each of those compilations against your sort of reference or your test case to see which one performs better. And performs better would, has various definitions, but one sort of tried and true definition of performs better is what finishes faster with the right answer, with on the same amount of resources. So so that's how you can sort of take advantage of this general optimization. Again, compile your code 3 times, run each of those against the same sort of test case, and see what finishes first. Okay, so moving on to our next items. So while these general optimizations can be applied to code running on any processor. There are also sort of specific optimizations in instruction sets that are only compatible with certain processors. On our Intel-based systems, so the Aurora system as of now has only Intel-based processors. So these are compatible with the AVX in AVX2 instruction sets. And these instruction sets allow for single instructions to be applied to multiple multiple pieces of data simultaneously. So one of the sort of common examples here, and this all falls into the area of sort of vectorization with code, and so SIMD and vectorization. But really what this means in practice is, let's say you're adding two vectors, right? And these two vectors are represented in your code as arrays. With this AVX and AVX2 instruction sets, you can sort of perform let me just back up. Whenever you're adding two vectors, the way that you can do that is to add the vectors sort of element wise. And with these instruction sets, you can perform that addition operation on multiple elements within a single sort of CPU cycle. So rather than sort of just adding sort of one element to another element in the vector in a CPU cycle, you may be able to get sort of 4 elements added in a single CPU cycle. So, you know, right there is a 4x speed up, sort of for nothing other than telling the compiler, hey, try to use the AVX2 instruction set. So again, same approach here. You would compile a code, you know, with different instruction sets and see what performs the best. So finally, moving along here at the bottom, sort of our third compiler optimization method is to try interprocedural optimization. And this sort of, like the different general optimization run levels, this is really a collection of different compiler techniques that the compiler will try by analyzing the entire program. So it's almost like it's a holistic sort of approach rather than the general optimization, which is sort of more piecemeal or more sort of focused on code blocks and single functions. So and also with interprocedural optimization, there's profile guided optimization. So this would be using actual sort of runtime feedback in order to select the particular optimization to take advantage of. So the compiler will, you know, run your code and then make decisions on optimization based on how your code performs. And again, this all happens with you throwing a couple compiler flags. So this sort of, that summarizes the low-hanging fruit sort of aspect. Again, these are something simple to try, really low effort on your end as the end user. Okay, so now sort of jumping into that simple to complex analysis that I mentioned. So starting off, before you would run anything new, you would start by seeing what information you can gather from previous runs. So this would be looking at log files, looking at trace job output to see where your job ran, how it ran, what resources it utilized. So sort of the next step up from that is watching processes run in real time. For that, you can use shop or top or PS, and there's some other commands as well. The next step up in terms of effort and complexity on your end would be to rerun your jobs with some extras to get some additional output. So user bin time is an example of that. Adding different print statements or looking at strace to capture sort of interaction of your program with the underlying kernel. And finally, sort of at the end of the sort of hierarchy here is instrumented runs. This is whenever you sort of you have a particular run of your job that is run solely for the purpose of running a debugger or a profiler. So we'll sort of delve into each of these here individually with looking at past processes. So whenever you run on an HPC system, you can gather information about what your job is using and what the underlying processes within your job are using in terms of resources. So how much memory is it using? How much CPU time is it using? How many threads are you intending to spawn, and how many are actually spawning, or how many processes are you actually spawning? A common occurrence, a common issue that a lot of people do face is sometimes they sort of unknowingly spawn way too many threads for the system that they're running on. So maybe they'll spawn 100 threads or 100 processes all running on the same node, and that can for CPU intensive tasks that can be very detrimental to performance, right? Because then you have a lot of processes running that are sort of switching on and off, and that can hurt performance. Trace job is a command that you can run to get an estimate in regards to how much memory you're using and CPU utilization and things like that. And the IAS Center can help you sort of utilize trace job. Again, yes. Go ahead.
Quick question.
Yes.
So, excuse me. So does trace job work with the singularity container and all that? So that's all good. I can get more output information with singularity.
Yes. So trace job, yeah. So trace job run is sort of at the job level. So really, whatever your job encompasses, whether that's a single core, a single node job, or a distributed job, or something running singularity, that will all be captured sort of at the job level with trace job.
Yeah, and that it'll still come out into the output file and everything, right? If I use singularity. Okay.
Yeah.
Sorry, just checking.
Yep.
Okay.
No, yeah, that's a great question. Yes.
Continue.
Sometimes, yes. Sometimes with the containerization, it can be a little bit sort of up in the air in regards to where you're running and
not very clear.
Yeah.
Yeah.
Yep. Okay. So the next step up, my Zoom is not sort of collapsing here. The next step up in that hierarchy is watching processes or watching your job in real time. And one tool that is very helpful for this is Top. And whenever we get into our hands-on example, I'll show you how you can use Top a little bit to get some useful information about the processes, the threads that you're running on a system. I have here that, so PS is another command that you can use to get information about what you're running on a particular system. So here, JMP579 is my user ID. You could run these commands with your user ID substituted in. We'll go through this process as well, but so in order to use Top or PS, you need to be connected to the node that's actually running your job. So in order to do that, you need to figure out where your job is running, and you can do that with the qstat-n1tu and then your user ID. And the last column reported from the output of that command will contain the compute node where your job is running, and then you can just hop over to that node with SSH and then run Top, PS, whatever other commands you want to run to sort of get some diagnostics on the processes that you're running. And again, we'll go through that in our hands-on example. I should note that you only have access to a compute node running your job. So as soon as your job is terminated, as soon as your job ends, you'll no longer have access to that node. And if you have an SSH connection established, that'll be killed off. Here's some helpful tips for Top and PS. It looks like we have some formatting here issues. Again, we'll see this in real time, but some things to look out for the states of your of your processes. So running is good. So hopefully your CPU intensive processes are in status running with a high CPU utilization. If you see D, uninterruptible sleep, typically this is associated with an IO sort of related issue. Either something can't read or write, and then so on and so forth here. Stepping along that hierarchy, the next step up is to rerun your job, rerun your processes with simple extensions. So user bin time is something you so user bin time -v is something you can sort of prepend to any command that you want to run, and that will automatically capture different CPU and memory usage information. You can also, so print statements is something else you can add in your code to capture simple things, but you don't want to sort of scatter various print statements all throughout your code, it's good to investigate simple things, but complicated things, print statements themselves can start sort of causing problems. strace is something you could prepend to the command that you want to run to capture kernel sort of interaction. And then ket segv is useful for memory-related segmentation faults. So finally, sort of at the end of our hierarchy is orchestrated runs. And so these are runs that you would conduct fully within a particular debugger or profiler. And debuggers and profilers have come with their own sort of spectrum. So we have tools that are entirely debuggers. We have tools that are sort of a mix between the two, and then tools that are traditional or completely profilers. And we see that sort of spectrum here. GDB is the debugger from the GNU project. And that's the one we'll use in our example today. DDT is a very nice sort of graphical. It's a debugger that has a graphical interface, and you can use that very easily to debug code that's parallel. It handles even handles Python and also GPU CUDA GPU code. So those are both traditional debuggers. In the middle is TotalView and in Valgrind. And then on the sort of end of the spectrum would be traditional profilers. VTune is one that is sort of the Intel-based profiler, gprof and Tal as well. So VTune has some nice examples here. If you're sort of just getting started with a profiler, since we're using, since our system is fully Intel, I would encourage to use VTune. So GDB basics. Again, we're going to see this in our hands-on example. I know I keep saying that many times, but so I won't go through this in incredible detail, but to use GDB, you need to compile your code with the -G flag. So debug symbols are included. And then all you need to do is just run GDB with the program that you compiled. There's different commands that you can run with GDB. So run will allows you to start your program. You can set breakpoints, which are portions, which are locations in your code that you want to sort of stop. You want the execution of your code to stop at that particular point. So you can say, break at line 582 in source file hello.world.c, and then the program will stop execution once it reaches that line. That will allow you to sort of conduct some analysis at that point. Step and continue are how you can sort of so step will allow you to sort of step line by line through the code, and note that this is the assembly code and not the source code that you wrote. So when you're stepping, sometimes you can sort of make a stepping move expecting to sort of go to one line in your source code, and then all of a sudden you're off in some other location, just because things can get a little bit out of order with the compilation process, especially if you're doing optimizations. So yeah, it sort of is what it is. Okay. gprof is the GNU profiler that we're going to use. To utilize that, you need to use the -pg flag or argument whenever, or option whenever you're compiling and linking. What you do is after you compile the program, you run the program as normal, and that generates some output, and then you run gprof to analyze that output. You'll find with these different profilers, there's many different options and many different items that you can track and look at. gprof is no different. There's something called the flat profile, the call graph, so on and so forth. And so sort of the basic run that we'll take a look at today, it follows this general syntax here that I'm highlighting, and that will give us the flat and call graph profile of our code. This is sort of a summary of the different items that we talked about here today. I'll focus in on the speeding up your code. Start with that low-hanging fruit with those compiler flags. You can, sometimes get pretty significant speed up for relatively, small effort on your end. With code, loop unrolling can be helpful. Cache optimization is something that can very much impact performance. In our matrix multiplication example that we'll see, while I don't go into detail about this, the reason that it performs so well is the reason that the naive example that we'll see performs so poorly is because it makes very poor use of the cache. Anytime you can so IO can certainly impact speed. So be aware of that. Use external libraries when you can, especially vendor optimize libraries, MKL. Whenever you're doing parallel computation, limiting communication, limiting that parallel overhead can serve to speed up your code. Okay, so finally, at our hands-on example, we're going to have two different test cases here. First up, we're going to have a factorial program, and we're going to pull down, we're going to clone a remote repo, which contains all of our examples. We'll talk about working with branches. We'll use make to compile our factorial program, and then use GDB to find a bug. And then we'll switch gears and take a look at a matrix multiplication example and profile that with gprof, which seems to be a typo here. This should say gprof, not drof, grof, I guess. So, I'm going to switch off to, yes, so I'm going to switch over to my, my terminal now. Hopefully everyone has a interactive session started. So hopefully everyone sees this, and you can click this blue button, and what that will do, it will launch you into a new tab that hopefully looks like this. If anyone sort of isn't at this point, please unmute yourself and let me know. Otherwise, go to Applications, System Tools, Terminal. That will open up a new terminal for you. Zoom in just so everyone can see. And what I'm going to do is I'm going to go into my Scratch directory. And over here, I'm just going to delete my ROR. So what we're going to do is do a git clone, and then we're going to clone the example file. So git clone, let me just sort of walk through my bash history here. Okay, so here's what you want to type in. And again, that's on the slides. So sorry, git clone. So git clone, and here's the address you want to clone. You'll see that will pull down everything, and you should now see a new directory in your Scratch. I'm just going to pause here until everyone can confirm that was cloned correctly. So Let me check the chat to see if anyone's having issues. Again, unmute yourself if you are. I don't see anything, so I will continue.
It says
Yes.
HTTP request failed.
Try doing module load git. And then HTTPS, I'll sort of highlight that here. So git clone.
Sorry, stupid question. Copy and pasting isn't working. I do control.
Yeah, so
work either.
So copying and pasting within the desktop is a little bit of a non-fun activity, I would say. So the way that you do that is within your desktop session. Hopefully, you see this little triangle, sort of this little triangle within this rectangle that I'm sort of hovering over my mouse here. If you click that, and then open the sort of clipboard looking item.
Got it. Thank you.
You can do that, and then so you would paste in there, and then you come back to your terminal and then sort of edit, paste there. That's how you sort of get in and out of pasting within this no VNC session that's actually running in the browser.
Oh, okay. Thank you. Appreciate it.
Yeah, it can be a little bit of a pain to say the least, but I guess that's the price we pay for having everything nicely in the browser. So hopefully that's cloned now. If we sort of take a look at our directory, we can see that here. And we see a couple of different examples. If you go to that repo on GitHub, it looks like this. And it sort of nicely walks you through the different examples. We're going to start here with this debug GDB example. So if you go there, here is the sort of steps we're going to go through. We just went through these steps. So now we're sort of on this stage. So so everyone can sort of go to this GitHub repo and sort of walk through these steps. You know, everything's laid out for you. I'll do it sort of in real time with everyone. But you know, if you're someone who just wants to sort of hit the ground running, everything that we're going to do is in this GitHub repo. Taking a step back, over on the terminal, I mentioned that I was going to show a couple things with top. So the first thing is sort of figuring out, let's say you submitted a job with QSub in a job script, and you want to see where that job is running. The first thing you want to do is qstat-n1tu and then your user ID. You can see I have a couple jobs running here now. This is a desktop job, and I can see that it's running on comp BC 0383. Since I'm already within my desktop job, I don't have to, you know, it doesn't really make sense to connect to that node again. You know, I'm already there. But let's say I wanted to connect to this batch job that I was running that happens to be running on comp SC 0195. I can sort of directly SSH there. Oh, SSH. Since I'm running a job there, I can connect, and once I connect, we'll take a look at top to see what's going on. So if I do top dash or capital U in my user ID, that will show sort of everything that I have running on the system. So you can see I have, you know, a lot of, you know, 20 Python processes running. This is running. So what are some things that we can see? So if we're looking at this sort of column-wise, on the left, we see the process ID of the various processors. We can see everything's owned by me because I ran top with that capital U option. This res, RES, signifies the amount of resident or physical memory my processes are using. We can see the S column, that's the state of my processes. So they're all in state R, they're all running, which is nice. They're all using, they all have high CPU utilization. This P column, which you may or may not have, tells us the core that the process is running on. And ideally, you want each of your processes running on a separate core. So I don't see any overlap there, which is great in terms of performance for my particular code that I'm running. So yeah, so that's a real quick sort of overview of some information you can get out of top. So I'm just going to back out of that here. Okay, so following along with our example, I'm going to enter into the debug GDB example. If I take a look at this README here, I'm not sure. Yes, so maybe I'll leave this up just so I can walk through it myself. I'm going to open up a different terminal. Okay, so module list. I'm going to load Git, and we're going to take a look at some Git commands. So if I do git log, this is going to show me all of the commits that were made to this particular repository. And you can see it's really a lot of commits from me, really just updating the README, and then the first commit. So git log will show you a history or a log of all the different commits that have been made to the repository. If I do a git status, that shows the current status of the repository. It shows if any changes were made and if those changes are being were made to files that are being tracked or not. So here we can see that there's a swap file that's currently untracked, and that swap file exists because over here I'm using VI to view the README. So this tells me that there's really nothing unchanged in this repository as of right now. You can view branches. Let me just sort of zoom in here. Okay, you can view branches with git branch. So you can see right now I'm currently on the master branch, and there's only one branch. If I do a if I go up one directory and do an ls-a, I see this .git directory. Whenever I just do ls, that's hidden. So this .git or .git directory is where all of the sort of Git magic lives. So the suggestion is never to directly edit anything in .git, rather to use the git commands to interact indirectly with those files. You can, if you would modify something in that .git directory incorrectly, you can sort of wipe out your entire, the functionality of your entire repo. So sort of know that it's there, don't delete it, that sort of thing. Okay, so I'm going to move back to my debug directory. And now we're going to first compile our factorial example. So I have here that we need to first load the GCC module. So I'm going to do that, GCC 5.3.1. And then I'm just going to run make. And so make uses a make file to compile the program. And if I take a look at that make file, this is a recipe to compile the software. So the syntax, these make files have their own syntax and layout, but essentially what is done in these make files is you define what needs to be made, a target, which is in this case, it's a factorial program. You define the dependencies of that target, which in this case are some object files, and then you define how those dependencies can be made. And these are just GCC statements to build those object files. If I take a look at this make file again, if I wanted to change the compiler, I could do that here by changing GCC to something else. I could add or remove compiler flags here, and that would be reflected sort of down below. Yes, so that make command compiled our program. We should see something else in this directory. Now we see a factorial program. So let's go ahead and run the factorial program. So /factorial, we'll run it. Calculate the factorial of. So here it's asking us for an integer. So I'm going to put 3. It tells me that 3 factorial is equal to 2. So if you recall, the factorial operation is, so this should be 3 times 2 times 1 should give us 6. This is giving us 2. So it seems like we have a bug or a problem in our code. And let's go ahead and use GDB to investigate that. So what we can do is use GDB directly with GDB factorial. That'll start GDB for us. Just for the sake of time, I'm going to sort of go directly to setting the breakpoint to where I know we should. The syntax there is break, and then the name of the source file, which in this case is factcalc.c, colon, and then the line number that you want to set a breakpoint at. So there I'm setting a breakpoint at line 10 of factcalc.c. And now I just want to run my program. So I'm just going to type run. So again, so what this is going to do, GDB is going to run my program until I reach that breakpoint or until my program sort of reaches the end. So I'm going to pass in 3 again. Okay, so now we have reached the breakpoint. We're at the specified line. So now let's just sort of step through and see what happens. So now we're stepping into a for loop in this program. Okay, so let's go ahead and print some stuff out. Let's print and see what counter is. So you can use P for shorthand notation or syntax for print, and then you can just start naming variables. So you can see counter is listed as 3. Input val is listed as 3. So let's step into this loop. So now counter should probably change. Okay, so now we're in the loop. Counter is at the initial value of 1. In this loop, we're setting output equal to the counter times itself. Right now, output is 1. So this first will be this first loop iteration will be 1 times 1. Let's keep stepping through. So now we're at a second iteration of this loop. So now counter should be, if I do a print on counter, it should be 2. And then if I do a print on output, it should be 1. Now we'll step past that. Now output should be, so now it was 2 times 1. We're at another iteration of our for loop. If we step into it, what happens all of a sudden, we are not going into another iteration of our for loop. We're immediately returning our output. And if we do that, we see that output is 2. We see that counter is 3, but we didn't enter into our loop, right? So the issue here is this our for loop condition. We're not entering into our for loop enough times to capture what the factorial operation needs to do. So that's the issue with our code. Okay, so I'm going to go ahead and quit the debugger. I'm going to say kill my process. I know what the problem is. I'm going to go right into that factcalc program, right to that line, and see what we can do. Oh, so before I do that, I want to do some items on Git with Git. Again, we're using version control on this, and we're currently on the master branch. So I don't want to make any changes to my production code, the main or master branch. I want to create a debug branch. So let's go ahead and do that now. So git checkout -b debug. So this command does 2 things. It creates a new branch, and it switches you over to that new branch. So now if I do git branch, we see we're on a debug branch. Now I will make the change to factcalc.c. We could either, there's a couple ways to fix this. One way is to just add a equal to symbol here to enter into that loop one more time. So I modified my source code. If I do git status, it should be telling us that, hey, you modified your source code. these files were just created through the compilation. They're not something we want to track. So we modified our source code. Let's go ahead and recompile that source code to see if it fixed the problem. So you can just type make, that'll recompile only the source code that changed. Now we can run factcalc again. So sorry, we can run factorial again. So if I do /factorial, now if I type in 3, hopefully it tells us 6, great. Okay, so factorial program seems to be working. So our debug branch has some changes that we sort of tested, and those changes seem to work. Let's go ahead and make a commit and save those changes. And the way you can do that is with this git commit command. And I'm going to put a commit message, which is fix for loop exit criterion. So this will help me sort of tie some meaning into the change that was made for the source code. So if I do, you have a question coming in?
Yep, we'll just go following down.
I'm not sure. I'm not able to hear you. I'm not sure if you're asking a question or if it was just some background noise there. Okay. Sort of continue on here. So I'm committing that change. So we see some git output saying that commit was made. Now, if I do git log, we'll see, hey, we have a new commit listed here. Okay, so now some other git commands that will be helpful. You can do a git diff to see the difference between the master branch and in this current debug branch. And it nicely highlights exactly what the difference is. You know, it's the for loop. Okay, so just to summarize, we had a factorial program that had a bug. We opened up a new branch. We fixed the bug in that branch. We confirmed the bug is fixed, and now we want to make those changes in our production branch, which is master. So one way we can do this is to now leave the debug branch. So if I do git checkout master, that will switch me back over to the master branch. And if I do a git merge debug, that will copy all the modifications from the debug branch over to the master branch. Okay, so now if I do git log and I'm on the master branch, we should see that new commit that was made. Okay, great. So this sort of completes our example here. We made a change and we got that change all the way into our production code, which lives in the master branch. Any questions on that? Now, if we wanted to, we could do a git push. We could do a git push and push those changes back up to the remote repository, but you won't be able to do that because you're probably not listed as a collaborator on the project. And I'm not going to do that now because I want to keep this sort of example intact without sort of the solution pushed up there. But you know, you can do just git push, and that would push that those changes back up to the remote repository. Okay, so we will sort of leave this directory and then go back and go through this profiling example with gprof. So I'm gonna go to that location over here. I'm gonna view the README. Okay, so this is an example that comes out of a course that is taught from UC Berkeley, which is part of the Exceed. I'm not sure what the title of the project is now, but through the Exceed program, a course offering through UC Berkeley is offered remotely at other institutions. and this example comes from that course. Not in its entirety, but the main sort of code comes from that course. So in this example, we are attempting to perform matrix-matrix multiplication, and we're doing that with sort of the naive the naive approach, which scales as sort of n cubed, where n is sort of the dimensionality of the matrix. This gets very costly as the size of the matrices increases. So what we're going to do is we're going to first compile the naive approach, which is essentially a nested for loop, which we can take a look at and see how poorly that behaves. Then we'll use the gprof profiler to figure out where what the issue is, where the hotspot is in that code, and then we'll swap that out with a vendor optimized library and see how that performance changes. Okay, so the first thing we need to do is module purge to purge out any modules that we have loaded. I'm going to do a module load Intel and MKL, and then I'm just going to run make. So that will compile everything for us, and then I'm going to directly run my my benchmark, which was compiled appropriately for gprof with the -pg flags, as we can see somewhere here. So -pg was here. So I'm going to run this example. Gprof, maybe if I can type, I will. Okay, so I'm going to run this example, and you'll see what this example does is it calculates the peak flops that are obtained for calculating for multiplying matrices of various sizes, and then it calculates a percentage value, and that percentage value is how close to sort of optimal performance is obtained. So you can see on average we're getting about 10% of optimal performance. And this sort of assigns a grade. So if we're getting a grade for this naive sort of order n cubed approach for matrix-matrix multiplication, our grade would be 14%. So not so great. So let's go ahead and profile our code and see if we can sort of identify any hotspots. So the command for that is gprof, and then the name of the program, which is benchmark naive gprof, and then the name of the output file that was generated from our initial run. And we'll see that generate some output very quickly. So we're going to take a look at this call graph. So we can see that in terms of the percentage of time, a huge amount of time is spent in this square underscore dgem function, which this dgem stands for double precision general matrix multiplication. So and up here with our flat profile, again, we're seeing this square dgem is taking all the time. Not a big shocker here in performing matrix-matrix multiplication. The function that performs matrix-matrix multiplication utilizes a lot of time. So if we just take a look at our code here, dgem naive.c, we can see our square dgem function is really, it's this naive approach with this nested for loops, which gets this sort of order n cubed scaling. So, the consensus from our run is this performs poorly, and maybe we can swap that out. And so that swap has been done for you in this dgem blast.c. So rather than writing our own squared dgem function, what we're really doing is making a call to a to MKL. MKL is Intel's optimized linear algebra library. So we're using their matrix multiplication function instead of one that we wrote ourselves. So if we run that code, benchmark-blast, we'll see we get much better performance. We'll see we're actually obtaining higher than 100% sort of usage, and this has to do with sort of Intel has something called sort of turbo clocking cores. So you can actually sort of, the clock speed can, if you're using a single core, the clock speed can be sort of pretty high. So now we're getting sort of a grade of 100 because we're getting, you know, over peak performance on this machine. And, you know, that sort of doesn't really make sense. It just, you know, you would say that if you're getting over peak performance, then your definition of peak performance is, you know, incorrect. But nonetheless, if, you know, if we would adjust this value, we would be getting very close to peak performance on this node. And, you know, really all we did was, you know, not going into the details, but what we did was we used gprof to identify that, hey, our matrix multiplier was consuming a lot of time, and then we just swapped that out for Intel's version of matrix multiplication, and we got much better performance across varying matrix sizes. Okay, so that wraps up our sort of contrived example for gprof. I will pause here and see if anyone has any questions. I'll check the chat. Looks like we have a couple coming in.
A quick question.
Sure.
I noticed when you did top, I noticed you ran some Python scripts on that other computer.
Yeah. Yes.
I know this is kind of contrived because most of these optimizations are for like C programming or C++.
Right.
Is there any stuff for like Python optimization or anything like that?
So I know the DDT is now owned by the ARM ARM, and they have an associated profiler. It's called MAP.
Okay.
Let me just try to bring module load DDT. If I just try to launch this, I know their debugger supports Python, so their profiler map may also.
Okay.
So I would try that, and then also there's many different sort of Python profilers out there. I can sort of I don't know many really outside of possibly ARM map outside of that, but you know, just like there's 20 different Python libraries to do something, there's 20 different Python profilers out there as well. But let me do a quick search after the session today, and I'll circle back to you to.
I was just curious off the top of your head, maybe if you, I can Google it myself, but you know, I was just curious because I saw you running Python, and I was like, okay, yeah. You know.
Yeah.
But no, it's okay. Thank you, though. I appreciate it.
Yeah, that's a fair question and something that I should look into anyway. So yeah, obviously feel free to Google it yourself. I'll do the same as well. And, you know, maybe together we can see what we can come up with. Maybe there's a consensus of, you know, what the best sort of community provided profiler is for Python. So. Yeah,
it's research. That's what it is.
Yeah.
So, yep.
Okay. Yep. Okay, so I'm going to switch back to the slides. So sort of timing wise, we have around 9 minutes left. So not enough time to go through all of the content, but maybe what I'll focus in on is I'll talk about some parallelization, point you to where you can find the hands-on sort of parallelization examples, and then wrap up with the quick scaling and where to go from here. Everything is sort of self-contained in that repo that you pull down. So you know, just because we don't explicitly go through the hands-on stuff together, everything is there for you to do it yourself. So you know, it's documented in a way to be sort of to stand by itself. So with that, I'll sort of quickly go through this. In terms of parallelization, stepping back, you need to sort of ask yourself some big picture questions. You know, how much time do you have to spend on this, and what can you gain from running across multiple processors? So, you know, how much time do you want to spend sort of possibly developing, you know, the code to, you know, maybe use MPI. So that Python code that we took a look at on that compute node is running using MPI through Python's MPI for Pi. So I made a decision that, you know, I could spend not a lot of time to get a pretty significant sort of performance speed up by using MPI, but by using distributed parallelization. But, you know, because the parallelism that I could expose in my underlying Python code was very significant. So I took a look at just with general timing information with the time it command, I was able to sort of narrow in. And maybe this is sort of a roundabout answer to your question with profiling. Sort of the poor man's profiling with Python is just the time it command, in my opinion. So I was able to profile my Python code and figure out that the majority of time was being spent in one particular area. And that particular area was very easy to sort of write in a way that I could distribute it across multiple machines using MPI in a way that none of those processes really need to talk to each other. So that's perfect sort of thing. That's like the ideal situation. But let's say you were sort of profiling or taking a look at your code and you identified, you know, a portion of your code that takes, you know, 10% of the time. You don't want to spend a year sort of working to accelerate 10% of your code, right? You know, that's not a good trade-off. So those are sort of big picture questions that you need to ask yourself, and profiling can help answer those questions. And obviously the underlying algorithm, how much parallelization you can expose, and the way that parallelism is exposed are important. Yeah, so different types of parallelization. I'll compare these to different food style distributions. So eating in a cafeteria, this is akin or analogous to multitasking parallelization. So everyone gets food at different times. They sort of come and go as they please, and nobody sort of inherently is required to share. So this, as we sort of step forward into diving into these different types of parallelization in the next slides, sort of keep this in the back of your mind. So multitasking, eating in a cafeteria. Shared memory parallelization is sort of analogous to family style sort of food distribution, where all the food is sort of at the center of the table. Maybe this is what people are doing for the upcoming sort of Thanksgiving holiday. People sort of grab the food that they want from the center of the table, but there's sort of the condition that you can't grab the mashed potatoes if grandma has them. You sort of need to wait. So family style shared memory distribution. And then formal dinner, this is analogous to distributed memory parallelization. So everyone has their own food. People can share, that they have to coordinate amongst themselves or communicate. People eat independently, but they can't move forward until sort of, they can't move on to dessert until, you know, the main course is finished. So diving into each of those, multitasking or multiprocessor jobs. So these are the easiest to sort of make parallel, because no task needs any information from another. Sometimes these are called perfectly or embarrassingly parallel sort of tasks or workflows. There's no inherent limit to the amount of RAM or processors you can use. It's really, what are the resources that you can take advantage of. So I used to run Monte Carlo simulations of gas absorption, and I would essentially run many different replicas of my system at the same time, and each of those would really just vary by a random seed. I was sort of trying to generate statistics so there I would maybe run sort of 1,000 copies of the same system. If I was running this in a serial sort of fashion, that would take me, let's say each of those take an hour, I'd be looking at 1,000 hours, right? But if I can run this on a system where I have access to 1,000 cores, I can get done, in an hour. So that's what sort of multitasking can do for you. So GNU Parallel is an example of something that can is a tool that can make multitasking very simple for you. You can essentially write a file of commands or jobs that you need to run, and GNU Parallel will take care of all the scheduling of that work and making sure it's distributed across the resources that you give it. PBS Dish is one, Python Pool, MATLAB has PAR4, and so on and so forth. So there's some tools that you can look into for multitasking. Shared memory, so multiple threads use the same memory, just like multiple people use the same sort of food at the center of the table. So this has an inherent limit to whatever is available on the node. So if you can only go up to a certain amount of memory, that's your blocker there. Shared memory parallelization is sort of arguably the next in terms of simplest to implement in terms of an existing code base. OpenMP is sort of a pragma-based shared memory implementation. It's sort of very widely used. And there you can see the different compiler flags for the GCC and Intel compilers. There's an example of GNU Parallel on the Git repo and also OpenMP. Finally, distributed memory. This is sort of your MPI. This is your workhorse of high performance computing for the last few decades. Each task has its own memory. There's sort of set points of synchronization or communication. Processes pass information back and forth. This can be the most sort of complicated the most involved to implement. I don't want to say complicated. I shouldn't say complicated, but it's generally the most work on your end as the sort of programmer. But you're not limited. You're only limited to the resources that you have. I mentioned so MPI is the workhorse of distributed memory parallelization, and there's many different implementations of MPI on our system, and you can pull down your favorite flavor. So we're not gonna have time for those hands-on examples, but if I go back to the repo, I can just sort of show you what those are. Here it is. If I go back here, we have an OpenMP example, which it's just a simple hello world. We have a similar hello world with MPI, and then a multitasking bag of tasks sort of example with GNU Parallel. And I think this uses, it runs some R code sort of using GNU Parallel. So all those examples should be self-contained with, tells you how to run the example. So let me know if you have any questions or issues when you do that on your own time. It looks like we're sort of almost past time for the time that we have. So I'm going to skip the scaling, but the information is there. Sort of in a couple of sentences. So scaling will allow you to sort of analyze how your program, how your code performs as you give more resources. So let's say you have a fixed problem size, and you want to see how that performance changes as you increase the number of resources. So maybe you have you run on 1 core, 2 cores, 4 cores, 8 cores, 16, and you sort of just keep increasing the number of cores, or 1 node, 2 node, 4 nodes, etc. And you analyze how the performance changes as you increase the resources. So that's an example of strong scaling. Weak scaling is sort of you're fixing the amount of work per resource. So if you have a problem size, if you have a given problem and you increase the number of resources by 2, then you also increase the problem size by 2. That way, the amount of work per resource it remains constant. So that's sort of scaling in a couple sentences. Here's some links to some resources for you and some information about some upcoming training next semester. So with that, I thank you for your time. I can stick around for a couple minutes if anyone has any specific questions.
Excuse me,
Yes.
I have a question. As you say, the OpenMP is used a shared memory system, and because the row supercomputer is distributed, so I just wonder if the OpenMP enabled code could be accelerated on the row.
Yes, yes. So ROR is a distributed system, but you can still run OpenMP or shared memory jobs on a single node. You just won't be able to take advantage of using multiple nodes. So OpenMP and shared memory parallelization is one, certainly compatible with the ROR systems. It's just with the caveat that you won't be able to take advantage of the fact that ROR has many nodes. You'll sort of be confined to a single node. That's not to say that people have hybrid approaches where they would maybe use MPI to distribute across multiple nodes, but within each MPI rank, which exists on a single node, they would use OpenMP to sort of in a shared memory sense on a single node. So a lot of projects use that sort of hybrid approach between MPI and OpenMP to sort of have the best of both worlds. But yeah, if you just have some shared memory code that you wrote, you can the thing for you to do would be to essentially access the largest node on our system. So largest node in regards to the most amount of resources, number of cores, the amount of RAM, and fully utilize that. Since you're with shared memory parallelization, you're sort of locked into a single node.
Yeah, another question is, I also have an MPI code, and when I try to apply for BART load, and the system rejects because it says open account cannot apply for too many codes. Do you know if there any upper bound of code then I can apply?
Yes. So the open allocation restricts you to 100 cores. So if you're trying to use more than that, whether you're trying to use 100 nodes, in each node you're trying to spawn 1 MPI rank, or maybe you're trying to only use 5 nodes, and on each node you want to spawn 20 MPI ranks. However you sort of dice it up, in the end you can at most under the open allocation only use 100 cores. Okay. So yeah, if you're receiving something sort of an error message or a warning when using the open allocation that you're sort of trying to use beyond the limits, that's the reason. The current limit is 100 cores. But I'm not sure if you have access to a paid allocation, but through paid allocations, you can gain access to resources beyond the limits of the open allocation. Yeah. Additionally, outside of the ROR system, for example, through the XSEED program, researchers at Penn State can gain access to additional resources, again, beyond the open allocation for free. It's just through the XSEED program that would be at a different location, not necessarily, it won't be at Penn State, it would be at an XSEED location. And traditionally, those are, for example, through Pittsburgh supercomputing with their Bridges system, or a system at TAC, or I think we even have some folks maybe using some systems at San Diego supercomputing. So if you're in a boat where the open allocation really can't meet your needs and you don't really necessarily have the funding to pay for a dedicated compute allocation, we can work with you to gain access to additional resources beyond the Aurora open allocation.
Yeah, actually, I have Googled the sleep system as you mentioned about, but it says that it's kind of grand, so we should people have to give their grant to use their system. So I cannot use that system because I don't have that grant.
Yes, so the Exceed program is sort of grant-based. So if you want time on their system, significant time, you need to sort of write a proposal and justify the use of that time. And as part of that proposal, you'll have scaling studies to show that, hey, you want to run your code and you want to run your code in a manner that's efficient. But before you get into writing those proposals, you can get access to sort of trial or sort of startup allocations, which don't necessarily require a rigorous proposal. So sometimes those, sometimes people can use those startup allocations just, sometimes they're enough for the research that you need to conduct, but if not, you can certainly use them as intended to sort of as a springboard to write a full grant proposal for that system. I can put you in contact. I can send you an email and put you in contact with the Exceed Campus Champions that we have on our on staff at the Institute, and they can work with you sort of through that process and get you started with get you or your PI started with a trial allocation and sort of get the ball rolling, if you will.
Yeah, sure, thanks.
Yeah.
Another question is you didn't mention the Open ACC, which use the GPU acceleration. So does your system also support OpenACC?
Correct. Yeah. So Roar supports OpenACC through the PGI compilers that we have on our system. So so if you have access to a GPU, and that would come only through access to CyberLamp or through a paid GPU allocation, you can use the PGI compilers to take advantage of OpenACC. Yes, so that is supported on our system, or any other. You're free to bring whatever you need onto the system in regards to compilers to be able to take advantage of OpenACC.
Okay.
And we also have for GPU we have CUDA installed on our GPU systems as well. So for folks that want to take advantage of, that maybe write their own CUDA code, that's compatible with the system as well.
Yeah, could I ask you another dumb question? I was kind of reading about user levels and permissions. If like I'm an undergrad, basically, do I still get access to like GPUs and CUDA type stuff, or is that just for ACI interactive in general? I can still access batch, I guess, right?
Yes. So every user has free access to our portal site, which I use, which we talked about, with these desktop sessions, and everyone has free access to the open allocation, which was 100 cores and 48 hours of wall time, and also the different file systems with the home work in Scratch. The only GPU that the sort of general free user has access to, let me show you, are if you come into the portal site here, and you want to get an interactive desktop job, and you need some sort of graphical base, you're going to do something graphical based. Maybe you have a program such as ANSYS that has a graphical front end. Then you have access to ACII, and that will get you a node that has a GPU, but that's a Quadro GPU. It's more for like graphics rendering. It's not necessarily for like raw compute.
Okay.
If you want access to
that's fantastic for what I'm doing. So
that's what you wanted.
it's
Okay.
good. Yeah. I just didn't. I was wondering what kind of hardware it was. I just didn't see it say anything. I was like, okay.
Yeah. So then this would be for you.
Okay. Thank you. Yeah.
Sort of just for completeness, if that wasn't the case, let's say you were sort of wondering about access to a general purpose GPU to compile and run CUDA code or OpenACC code.
Yeah.
Then as I mentioned, you would need to have access to CyberLamp, which is sort of a dedicated GPU partition, or we have GPU nodes that are available for GPUs available for purchase, like a paid allocation.
Yeah, I see. So I noticed your associates program has been cut off. Is that how you usually pay through those GPU?
No. So any Penn State faculty member can purchase an allocation. So you don't have to. Yeah, you don't have to be a associate or a faculty fellow. Just as long as you're a faculty. Just as long as you can tie yourself to a faculty member. So you mentioned that you're an undergraduate. If you're a research advisor or whoever, they want to collaborate. If sort of someone along the line can purchase a GPU allocation, they can let us know that they want to give you access to that.
Oh, okay. I got you. Okay.
Yeah.
So I need to get permission basically, and
yes. So if you know a researcher that already has a paid allocation on our system, you can work with them to sort of get their permission to gain access to their allocation.
Oh, okay, I see. Thank you. All right. Would you know if associations are opening up again anytime soon, or?
I'm not sure what is being done with our associates program. That's something I can follow up with you on as well.
Oh, okay.
I can check into that.
Thank you so much. But yeah. All right. I just want to say thank you. I do have to go. It's very late.
Yep.
Yeah.
Oh,
thank you so much.
Yeah. I appreciate you attending. Thanks very much.
Yeah. Bye.
So your point is the high-end GPU, like the K40, is only open for the paid services, not for right?
Yeah, so we have let me go somewhere here where I can show you. Okay, so we have, let me just make sure. Are you seeing my terminal by chance?
Yeah.
Okay. So let me comp test GC. I want to go to a GC node. I want to go to a GPU node, but I just want to make sure no one's using it. So if I go to comp, if I hop over to one of our GPU nodes, I can show you what we have there in terms of hardware. So if I do NVIDIA-SMI, oh, not found. That's not good.
Okay.
We have nodes that have dual K80 cards. So two K80s, NVIDIA K80s, and then we have nodes that have two P100s, NVIDIA P100s. That's what we have in terms of available for purchase on the ROR systems. On CyberLamp, which is sort of a NSF-funded partition, they have nodes that have a single P100 card, and then they have a few nodes that have 4 P100 cards. That's the extent in terms of the GPUs that we have available currently on our system.
Okay. Because I run my OpenACC code on the row system, and the acceleration is not very good, and so I try to apply for the high-end GPU load, and it takes more than 1 week, and it makes sense that it's not open for open accounts.
Yes. Yeah, so which GPU did you utilize to run your code?
You say which GPU?
Did you use like an interactive desktop, like one of these?
Yeah, I tried this, but this acceleration is not very good.
Yeah, that's going to be that's going to be bad because it's a NVIDIA Quadro card, and you're sharing it with many other people. So yeah, I'm not surprised to learn that didn't work out very well. In terms of, were you able to gain access to a GPU allocation or not yet? You're still trying to work on that.
Sorry, I didn't understand.
So you had mentioned that you were able to test on one of our sort of ACII nodes, but were you able to test on another node on our system, or not yet?
I made the application, but I'm still under queue for more than 1 week.
Okay, and where did you submit that application?
In the open, in the ACII node, just like you showed us in the terminal.
Oh, you have a job. You have a okay.
Yeah. Correct.
What's your user ID by chance?
WUM
W.
68. WUM.
Oh, M.
Yeah, correct.
Okay, GPU test. Okay, so yes, so that's the problem. You're trying to submit to the open allocation, and unfortunately, as of now, the open allocation doesn't have any GPUs.
Okay.
Yes,
Okay.
so this job is going to sit there forever because yeah. So what we can do is, are you a faculty member or a student, staff member?
Yeah, I'm a postdoc.
Postdoc. Okay, so I will follow up with you, and maybe what we can do is get your direct PI to request a trial GPU allocation, and that will allow you to test the performance of your code on some GPU nodes in order to determine whether it's a good decision for your group to purchase a GPU allocation.
Okay, that would be great.
Yes, so this would be, and it depends on the availability of the node types, but this will give you at most a sort of a 30-day trial allocation for a GPU node to test the waters, so to speak, test the performance, and then afterwards you can determine whether it's a good purchase decision for your group or not.
Yeah, that would be great. And I saw then if I want to purchase sometime, it's the fee is calculated per hour, but usually I just you can see here this task just for several minutes because I just want to do some benchmark tests. So even if I just do some several minutes benchmark tests, the fee will still charge per hour, right?
So we don't have a credit-based model. We have sort of, your PI would purchase a set amount of cores and set amount of GPUs, and you would have access to those for a set fee for a certain amount of time. So you would be able to fully use those resources that you purchase for the entire amount of time that you purchased or your PI purchased, or alternatively, you could not use them at all. In both cases, you would be charged the same amount, if that makes sense. So it's different from sort of credit-based models where you say, you would purchase 1,000 hours and you would use them whenever you need them. It's sort of, you purchase a resource and you have access to that resource for some amount of time.
Okay, understood. Yeah.
But with the trial allocation, yeah, you're free to do these little quick hitting sort of benchmark runs. That won't be a problem or anything like that. So.
Oh, that would be great. That would be very helpful. Thank you very much.
Okay, so I will follow up with you sort of independently on two things. One, for the Exceed program, I'll look to get you in touch with our campus champions, and they can work to get you access to an Exceed system. And then I will put you in touch with someone from our sort of project management team to work with you. But ultimately, it's going to have to be your PI to request a trial GPU allocation.
Mm-hmm. Mm-hmm. Okay.
So would you happen to have the your PI's user ID?
Yeah, sure. It's DHW.
Okay.
Yeah.
Oh, just no number. Okay.
Yeah.
So that must be an old username.
Yeah.
Yeah. Back in the day, they had shorter name. Okay, so great. So I will follow up, and I think that's everything. Unless you have any other questions, feel free.
Nope. Thank you.
Yep. Okay. Thanks for joining, and I'll be in touch as I mentioned.
Thanks. Have a good day.
You too. Thanks. Bye.